So for in continuation with the above table that we have drawn from two stage n-bit type DACs, we can finally write the maximum and minimum value of resistances R. We can write R max to be equals to R1 for value n1 lies between 2 to n upon 2 and n1 minus 1 upon R for the value n upon 2 less than equals to n1 then equals to n minus 1. This is the value of R max. Because why we are determining these values? Because we want to know the spread in the resistance for two stage n-bit type DACs, spread in resistance. Similarly, we can determine the value of R minimum is given by R for value n1 value less than equals to 2 n minus 1. Similarly, this value is R1, value is lying between n1 equals to n minus 1. If we summarize, so this is the summary of all this discussion that we have determined. So the value of R1 can be written again, though we have already given the value of R1, just for a reminder I am writing the value of R1, which was 2 to the power n minus 1 minus 2 to the power n1 minus 1 upon 2 to the power n1 minus 1 times R. Okay, so this is the value of R, this we have taken. So finally we can write the spread value, spread in the resistance. How we can write spread can be given by R max over R min, can be given by R1 upon R for the values n1 lying between 2 and n upon 2 for the value n1 minus 2 to the power n1 minus n lying between n1 less than equals to n minus 1 and n2. Similarly, we can write 2 to the power n1 minus 1 upon r1 upon r, where n1 equals to n minus 1. This is equation number 1, and this is my spread value of resistances starting from minimum to the maximum value for different values of n1. n1 is the single stage that we have, for which we have determined the Norton equivalence. So here is the n1, there is n1. For different values of n1, we have different values of this resistance values. Okay, so this is the conclusion of two stage n-bit type. Okay, now let us see the next point we are going to discuss is the next topic is that we will discuss today is multi-stage weighted resistor DAC. We are going to discuss multi-stage weighted resistor DAC. Okay, that we are going to discuss. So what we are having in multi-stage DACs, in multi-stage DAC, from figure 4.5b, again I am using this 4.5b figure. This is my figure 4.5a. earlier this is my figure 4.5b. so in reference to the figure 4.5b, we can replace DAC D2 with another two-stage DAC with two-stage DAC. So this process may be continued. This process may be continued until we get the last DAC value as 2 or 1 bit DAC. This is our objective. So this process will continue for multi-stage. We are using the same stage, same two stage DAC. The only difference is that we are repeating this cycle. How? For what purpose? For to get the last DAC bit to be equals to 1 or this 1 bit DAC. Okay. So these multi-stage DACs will be designated as N1, N2, N3, Nk up to NL, the last stage. NL refers to the last stage DAC. So I will show the pictorial diagram how these DACs will work. The maximum number of DAC, the maximum number of stages in DAC occurs when there is a condition. What is the condition? All NS have minimum possible values of 2. They will have all minimum possible values of 2 except the last stage, where the values is equals to 1. Okay, so we have to reach up to this last stage using the multi-stage filter. So we are decreasing the values from higher value to the lower value. Okay, this is my objective. So let us draw the diagram of this DAC. So in a nutshell, this format can also be written as DAC of which type? From 2 up to 2 or the last stage 1. This is my requirement. This is the final. So we can draw this circuit as, suppose there is a resistance R1. This is my N1 stage having the input value B0 to Bn1 minus 1. The resistance R2, the second stage N2, the input values again Bn1 to Bn1 plus N2 minus 1. Similarly, we will have the last stage NL. So this is my value of RL, the value is NL, where the signal value will be Bn minus L up to Bn minus 1, and this will be connected to the VG, the virtual ground point. Okay, so this is ultimately known as the L stage DAC. This is known as L stage DAC. So we can write the total number of multi-stage DACs. It can be written as the total number of multi-stage DAC, in which the total number of n-bit multi-stage DAC can be shown like n minus, not n minus, n DAC. This is n DAC, n type DAC equals to n minus 1 DAC plus n minus 2 DAC for value n greater than 2. What is the significance of writing this pattern? The significance of writing this pattern is that we are writing how much value? If we are writing nx DAC, it means what does it mean? All possible number of x bit DAC, which can be written as n1 DAC up to n2 DAC, and the last stage to be equals to 1, starting from first to the last stage. This is my last stage. So for example, the number of possible DACs for n equals to 1 to 12 bit can be given as if we have a stage n, so these are and this is n bit total number of DAC. So if stage is 1, this is 1, stage is 2, 1, this is 3, this is 2, this is 4, this is 3, this is 5, this is 5, this is 6, this is 8, this is 7, this is 13, this is 8, this is 21, this is 9, this is 34, this is 10, this is 55, this is 11, this is 89, this is 12, and this is 144. So initially you see the values of n bit, the number is small, but as soon as the stage increases, this number increases exponentially. So this is the basic advantage of this n bit type or L stage type DAC that we want to have from the programmable gain amplifier. So this is all about n stage type DACs. Thank you.